Hello everyone, this is Professor Roman. Let's continue the ring theory lectures. Let's conclude our discussion of Euclidean domains by a closer look at the Gaussian integers. We have seen that the ring of Gaussian integers is a Euclidean domain under this Gaussian norm, which is again the square of the complex norm, and that the units of the Gaussian integers plus and minus, positive and negative 1, positive and negative I. The ring of Gaussian integers plays a significant role in the branch of mathematics known as algebraic number theory. For example, the Gaussian integers play a role in determining the nature of Pythagorean triples. Those are triples x, y, z, for which x squared plus y squared equals z squared. It also plays a role in determining which positive integers are the sum of two squares. Our goal here is to determine the prime elements of this ring, and they are known as Gaussian primes. But we need to start with a preliminary result from number theory. And it is called Wilson's theorem. We talked about it in the group theory lectures, actually. An integer p greater than or equal to 2 is prime if and only if p minus 1 factorial is congruent to negative 1 mod p. As to the proof, if p is greater than or equal to 2 and prime, then this set, Zp, is a field under addition and multiplication mod p. If capital Pi is the product of the non-zero elements of Zp, then capital Pi is not quite equal to p minus 1 factorial, because that may exceed p. We have to reduce mod p to get it into Zp. So this is a congruence. Now, we can group the elements of Zp into two groups, the involutions and the non-involutions. The product of the non-involutions, however, is equal to 1, because every non-involution is different from its inverse, and so when you take the product, all the involutions and their inverses will appear as separate factors, and they will cancel. So capital Pi here is just the product of the involutions in Zp. But the involutions are roots of this quadratic polynomial over Zp, which is a field. This is where being prime is critical. And just like the polynomials over, say, the real field, a quadratic polynomial has at most two distinct roots. And we're actually going to prove that in the next chapter. So in the present case, these roots are positive and negative 1. So these are the only involutions. So when you take their product, you get negative 1. The converse is quite simple. If this does hold, then p divides p minus 1 factorial plus 1. Now if p should be factorable into a times b, where a is bigger than 1 and less than p, in other words, if p is not prime, then a will also divide p minus 1 factorial plus 1. But a being less than p will divide p minus 1 factorial, therefore it would have to divide 1, and that is a contradiction. So p must be prime. That's Wilson's theorem, and it's going to be very handy in a minute. So one place to start the search for Gaussian primes is first to determine which integers are Gaussian primes. The integers form a subset of the Gaussian primes. Now, if an integer is not prime, then it's not a Gaussian prime. But if an integer p is, let's say, not a Gaussian prime, so p is now a prime integer, is not a Gaussian prime, then it has a non-trivial factorization over the Gaussian integers. It's a prime, p is a prime integer that's not a Gaussian prime. Those are not the same thing. Prime integer, Gaussian prime are different because we're in different universes. Okay. So p does have a factorization over the Gaussian integers if it's not a Gaussian prime, a non-trivial factorization. So the norms of these two factors are greater than 1. Taking the norms gives us this, and since p is a prime integer and these are integers, and neither factor is equal to 1, both factors must be equal to p. And so p is the sum of two squares. Conversely, if a prime integer is the sum of two squares, say p equals a squared plus b squared, then we can easily factor it over the Gaussian integers in a non-trivial way. So we have shown that a prime integer p is a Gaussian prime if and only if it cannot be written as a sum of two squares, two square integers. Okay. So that's a complete characterization of the prime integers, or I could say the integers that are Gaussian primes. But it's not necessarily a practical result, because you have to check to see if something's a sum of two squares. There is a simpler, from a practical point of view, much simpler characterization. And it comes from, as a corollary to, a theorem of Fermat. An odd prime p is the sum of two square integers, and that's obviously relevant, if and only if p is congruent to 1 mod 4, something very easy to check. Odd primes of this form are known as Pythagorean primes. So as to proof, a simple parity argument shows that if p is the sum of two squares and it's an odd prime, then it's congruent to 1 mod 4, and I'm going to leave that for you to sort out. Parity argument means check what happens if x and y are even, odd, the same, different. For the converse, suppose that p is an odd prime that is congruent to 1 mod 4, so it's 4k plus 1 for some positive integer. We want to show p is the sum of two squares. And this is where Wilson's theorem comes to our aid. It says that 4k factorial, which is p minus 1 factorial, is congruent to negative 1 mod p. That is to say, p divides 4k factorial plus 1. Now, if we can write 4k factorial in a special way, first of all, it's the product of the numbers from 1 to 4k. So here is 2k and 2k plus 1 and so on. These are all congruences mod p. 2k plus 1 is congruent to negative 2k mod p. And 2k plus 2 is congruent to negative the quantity 2k minus 1 mod p. If you add 2k plus 1 and negative, if you subtract, negative 2k, you get 4k plus 1, which is p. So it's congruent to 0, and so on. So by altering the last half of the factors, we get negative 1 to the power 2k, because there are 2k factors with a negative sign, times 2k factorial squared, because there's 2 copies then of 2k factorial if you pull out these negative signs. And of course, negative 1 to the 2k is 1, and so you get 2k factorial squared mod p. So if I call 2k factorial m, then 0 is congruent to 4k factorial plus 1, which is congruent to m squared plus 1 mod p. I probably should have parentheses around here. Okay. Well, that means p, another way to say it, p divides m squared plus 1. Therefore, over the Gaussian integers, we can write p divides m minus I times m plus I. So p cannot be a Gaussian prime because it doesn't divide either of the factors. So p is the sum of 2 squares. As a corollary to this result of Fermat, and looking back at this previous result, we see that a prime integer p is a Gaussian prime if and only if it's not congruent to 1 mod p, and since it's got to be, it's either odd or 2, therefore it has to be congruent to 3 mod. Did I say mod p? Mod 4. Okay. If you take out the case p equals 2, it's not a Gaussian prime, and it doesn't satisfy this, so that's okay. And then if you think of the rest of the primes, they're odd, so they're congruent to either 1 or 3 mod 4, and we've just ruled out them being congruent to 1 mod 4, because then they'd be the sum of 2 squares, and so they're congruent to 3 mod 4. So you can't get any nicer description of the prime integers that are Gaussian primes as well than this. Since the associates of a Gaussian prime are also Gaussian primes, this corollary tells us that among the Gaussian integers, alpha equals x plus yi, where either x is 0 or y is 0. I guess I should say non-zero Gaussian integers. I don't want them both to be 0, otherwise alpha would be 0. Among these, so these are either real numbers or purely imaginary numbers, because one of x or y has to be 0. Then the Gaussian primes are positive and negative p and positive and negative ip, where p is a Gaussian prime. In other words, p is a prime integer congruent to 3 mod 4. So we know which integers are Gaussian primes and which elements of the form ip, where p is an integer, are relatively prime, are Gaussian primes. Okay, what about the Gaussian integers alpha equals x plus iy where neither of x or y is 0? Well, if alpha is not a Gaussian prime, we can do something similar to what we did before. Alpha then factors into non-trivial factors, so these norms are greater than 1. Taking the norm gives us this, and so we see at least that the norm of alpha is not a prime integer. Okay? So if alpha is not a Gaussian prime, its norm is not a prime integer. So if its norm is a prime integer, then it is a Gaussian prime. Conversely, suppose that alpha is a Gaussian prime. Again, we're assuming that x and y are non-zero. Norm of alpha is alpha times its conjugate. And since the conjugate is also a Gaussian prime, I'll let you ponder that, this is the essentially unique prime factorization of the norm. Now, if the norm is not a prime integer, then it has a non-trivial factorization, m times n. These are integers now. We're factoring in the integers. But in the Gaussian integers, since alpha is prime and it divides the integer product here, mn, it must divide one of the factors, let's say m. And so alpha bar will have to divide n. It's got to divide one of the factors as well. They can't both divide m. So we can write m as beta alpha and n as gamma alpha bar. Beta and gamma are in the Gaussian integers. I know it's a little hard to keep track here. There's two universes, the integers and the Gaussian integers, and it's important to keep the species straight here. It follows that alpha alpha bar, which is the norm of alpha, can now be written as beta alpha gamma alpha bar. Well, this tells us that beta times alpha is a unit, and therefore beta and alpha are units. And in particular then, alpha and m, is this equation here, are associates. So alpha is one of the associates of m, and those are the units times m, so it's positive negative m, positive negative im. But alpha can't be in this set because alpha has non-zero real and imaginary parts. So we have a contradiction which tells us that the norm of alpha is prime as an integer. And so to conclude, we have a very nice characterization of Gaussian primes. So let's say alpha equals x plus yi. If xy equals 0, so at least one of these coefficients is 0 here, then alpha is a Gaussian prime if and only if it is positive negative p, positive negative ip, where p is a Gaussian prime. It's an integer. So it's a prime integer congruent to 3 mod 4. If xy is not 0, so alpha has non-zero real and imaginary parts, then alpha is a Gaussian prime if and only if its norm, x squared plus y squared, is a prime integer. And that will do it for our discussion of Euclidean domains.